In this video, we're going to cover section 3.3 on Bronsted-Lowry acidity. And we're going to use a quantitative perspective to describe the relative acidity of organic compounds. In the following video, we'll cover acidity, but use a more qualitative perspective. In the quantitative perspective, we're going to have a numerical value that represents the relative acidity of organic compounds. And that value comes about by examining the equilibrium that exists between the reactant states, that is, our generic acid in the presence of our base water, and the product states, which shown here is the counter ion or the conjugate base of that original acid, and the hydronium ion, which is the conjugate acid of the original base. Now, an equilibrium is a state in which there is no longer an observable change in the concentrations of reactants and products. And so you'll notice that the arrows that we use to describe an equilibrium are these half-headed arrows, one pointing in the forward direction and the other pointing in the reverse direction. And so what these arrows imply is that this reaction is reversible, meaning that although this acid will donate its proton to a water molecule to form the hydronium ion and leaving the acid as its conjugate base, the counter anion, there is the possibility that these products can react to give you back your reactants. And so we're looking at a relative percentage, if you will, or concentration specifically of the products relative to the concentration of the original reactants. And so we can measure this particular variation or ratio of products to reactants in this way. And so when we take the product of the product concentrations and divide that by the product of the reactant concentrations, we come up with a value that we use to describe this equilibrium. And so this uppercase K subscript EQ is referred to as the equilibrium constant. So for acids, we will often describe this equilibrium in terms of the dissociation of the acid. And so Ka is used to describe the dissociation of the acid to its hydronium and conjugate base. Now, these Ka values being quite large or quite small, we often will convert these to a log scale for simplicity. So if we take the negative log of these Ka values, we end up with what's called the pKa. And we will quantify the acidity based on these pKa values. Now in this course, we're not going to be calculating pKa values, but I think it's important to be able to appreciate what the relative values, pKa values, say about the relative acidity of organic molecules. So in your textbook, there is table 3.1 that lists the pKa values of some common compounds as well as their conjugate bases. So as you can see, the strongest acids are going to have the lowest pKa values. Recall that the strongest acids will dissociate most efficiently. And so as a result, their Ka values will be quite high. But when you take the negative log of those Ka values, the result is a negative value. And so you can see that our stronger acids are inorganic acids such as HCl and HI. These all have pKa values that are well below 0. And remember that pKa values being a log scale, when we look at a difference of 2, this represents a factor of 100. So we would say that sulfuric acid is 100 times stronger than HCl based on these pKa values. Now, I don't want you to worry about memorizing any of these pKa values. These are presented for your reference. But again, it's important when we're discussing the relative acidity of organic compounds to have some general sense of where they lie in these tables. So you can see that, for example, carboxylic acids such as acetic acid or ethanoic acid, as it's known with its IUPAC name, has a pKa value of around 5. So that's the main constituent in household vinegar. And as we proceed to lower acidities towards molecules like water and the alcohols, we see that our pKa values are significantly higher than those for the acids. And what's also important to recognize is that the strongest acids, the conjugate base of the strongest acids, are some of our weakest bases. So there's a sliding scale that as we proceed from a higher pKa value to a lower pKa value, we are increasing the acid strength, but the conjugate base of those acids are becoming weaker. So the opposite is true, is that as we proceed to, let's say, the alcohols, which are much less acidic than our inorganic acids and sulfuric acid, the conjugate bases of those alcohols are some of our stronger bases. And finally, as the last section in this table, you can see that when we look at some of the weakest acids, the weakest that we'll discuss, that of the alkanes, that when an alkane loses a proton, these alkanides are quite strong. These are some of the strongest bases and used as often as proton transfer reagents to deprotonate various other organic molecules. These are quite strong because, again, the conjugate base is going to be determined by the relative strength of the acid. Now, one rule of thumb that is quite helpful with these acid-base reactions is that this equilibrium between reactants and products will always favor the formation of the weakest or weaker acid. So we can assess, based on the relative strength of the acid versus the conjugate acid, which direction the reaction will favor, which direction the equilibrium will favor. So in this example where we have ethanoic or acetic acid reacting with the hydroxide ion, again, we can use our curved arrows to represent this proton transfer. And the net result of this reaction is the formation of a molecule of water, the conjugate acid, and its conjugate base, the acetate. Now, if we look at the relative strength of the two acids, the first acid, the original acid in our reaction, our reactant state, is the acetic acid. It has a pKa of 4.75. The conjugate acid, which is water in this example, has a pKa of 15.7. So when we compare the relative strength of the acid to the conjugate acid, clearly the conjugate acid is weaker by 10 orders of magnitude, so 10 to the 10. So that is why the arrows are drawn in this manner, is that we give a shorter tail to the arrow in the reverse direction from right to left, because the likelihood of the conjugate acid and conjugate base reacting in appreciable amounts to reform the original acid and base is quite low. So it's a very small percentage of original acid and base present when you have such a difference in pKa values between the conjugate acid and the original acid. So we would say that this reaction is favored in the forward direction, and we can confirm that quantitatively by comparing the relative pKa's of the conjugate acid with that of the original acid. Now, for some reactions, because the pKa values are so vastly different, the reaction is generally not treated as an equilibrium process, but rather as one that goes to completion. And so we'll use a different type of arrow to describe these reactions where the likelihood of a reversible reaction is quite insignificant. So in this example, we have some of the strongest bases that we know of, which is the conjugate base of some of the weakest acids, the alkanes. If this alkynide, as shown, reacts with a molecule of water, it's going to form some of the weakest acids we know of, the alkane. And the resulting conjugate base of that original acid, the water molecule, is the hydroxide ion. Now, if we look at the relative difference in the pKa's, we see that there's over 30 orders of magnitude different between that of the conjugate acid, the alkane, which is roughly around 50, and that of a water molecule with a pKa of around 16. So pKa values are useful for describing the relative acidity of organic compounds, and they also provide a perspective in terms of the reversibility of a reaction. When pKa values between the acid and the conjugate acid are not too different, there's a good chance that there's an equilibrium that is established between the reactants and the products. Whereas in cases where the pKa values differ quite significantly between the acid and conjugate acid, we often will refer to those reactions as being irreversible. So if you have any questions with respect to pKa values, by all means send me an email or start a discussion in our forum. Thank you.